Yeah.
Hey everybody, welcome to Cleared for Takeoff. Cleared for Takeoff is a student-run interview series featuring aerospace professors, professionals, and students, focused on sharing real experiences in research, academics, and industry. It aims to give high school students clear, practical insight into pathways and careers in aerospace engineering. Today we're joined by Professor David Barnhart, Director of USC's Space Engineering Research Center and former DARPA Program Manager, whose work focuses on a new generation of spacecraft, satellites that can be built, repaired, and reused right in orbit instead of made once and thrown away. Thanks so much for joining us and welcome to Cleared for Takeoff.
Cheers. Pleasure to be here.
So, for our first question, you started out in aerospace engineering, spent more than a decade as a civilian engineer in Air Force research labs, then moved through DARPA, co founded new companies, and ended up running a research center at USC. That's obviously a winding path through like government, startups, and academia. So, what carried you from one stage to the next, and what were your takeaways from each stop?
Yeah, interesting. So some might say that I just can't hold a job, right? That's one idea.
Yeah.
I honestly it was curiosity and I think the thirst for new experiences for innovation. So that was really the big thing. Each opportunity specifically was unique, and I chose to go down different paths from the government side, from a laboratory, to starting up a company in the same domain, and then going down the academic path. Um, all because at each stage there was an interesting potential opportunity that I saw or thought that I could realize by taking that next step.
Yeah. Thank you.
So we wanted to move on to the next question. Your work sits at the intersection of a few things: space robotics, satellite design, and assembling structures in orbit. So they all fall under this idea that you like to call second generation space. How do those pieces fit together, and how would you describe it to someone who's never heard of the term on orbit servicing?
Yeah, no. Uh, the simplest way to sort of, at least I try to characterize it, is that every platform that is on the Earth, whether it's a ship, whether it's a car, whether it's a plane, whether it's a building, it doesn't matter. The structure is built, and then over time we have the ability to maintain it, upgrade it, repair it, sustain it, right? So it's a concept that we use every single day, and it's been used for almost 1,000 years. Yet
Mhm.
the one domain that we did not start down that path was in space,
Mhm.
and the specific domain of space servicing, in essence, is just bringing space into the same domain that every other platform on the Earth is able to exercise, from maintaining, upgrading, refueling, etc. Now we're transitioning it into space.
Wow.
Thank you.
Yeah.
So for our next question, most people assume that when a satellite runs out of fuel or breaks, that's just the end of it. You just build a new one and launch it, but your whole field pushes back on that. What actually happens to satellites in orbit today, and why is building them as one and done machines such a big problem?
Yeah, no, it's a good. So it's interesting because there's a bit of economics along with sort of technology that you have to sort of look at. Um, we there is no question that in again, if we use the example of the Earth and any other domain today, we do throw a lot of stuff away. We might use it once and then we might throw it away. All right. A
Mhm.
lot of it depends upon how expensive it is to be made, how easy it is to be made, the materials, the properties to be made, etc. Um, Space is one of those really interesting domains that it's pretty harsh. Um, Zero gravity is one; you got to deal with that. Two, the temperatures are incredibly extreme, one way or the other. So when you combine those things together, that means you have to really work hard to build something that's going to last in space. Now, the interesting thing is that over the years, commercial technology, specifically microelectronics, has gotten so much better that it's now able to work and operate in those harsh domain of space, whereas years ago it wasn't able to. So they
Yeah.
had to build spacecraft to really, really, really last and put a lot of shielding around, etc. Now, what's fascinating is we're using the advances in technologies on the ground, applying them to space. And then the other interesting thing is that once a spacecraft gets up there and it actually works, um, it typically lasts much longer than the original design life because there's no once it's working within zero gravity, within the radiation, within the temperature, it's going to maintain itself. Um, the the challenge, however, is that the cost to get things up there is so high, and so there was the economics that have now shifted. Interestingly enough, primarily from one company, SpaceX, has really opened up by lowering the barrier of entry for how much it costs to launch a satellite per kilogram. Now many people can send satellites up there. So what's fascinating is there's this there's this incredible balance and dichotomy that's occurring. On one hand, the launch costs have gone down to the point that we can now uh, even go further in terms of one and done throwing away things in space because they're so cheap.
Hmm.
On the other hand, space is a domain, particularly that has, I refer to it in some cases as harbors or, oceans, and those are basically orbits.
Yeah.
Low Earth orbit lends itself to things that throw away very quickly.
Yeah.
The further out you go on orbits, the things are going to stay up there so much longer. And so, therefore, it makes far more sense now to apply the precepts that we have on the ground, which are maintaining, refueling, upgrading, to something that you put up. You spend a lot of time and a lot of money, and it's still very costly to launch it to the outer orbits. So that then makes sense for you to actually do space servicing. So it's an interesting approach. Now's the time for technology that we've created to do servicing in space.
Hmm.
Launch costs have gone down. More people are going into space. Depending upon where they go, now it's making far more sense to actually do servicing. So it's transitioning from an industry that integrates things on the ground and launches it to now one that can integrate things in the domain that it's operating in.
Thank you. And I know
Long
you,
answer to your question.
yeah. And I know you said like about a lot about like how things in like the higher orbit they kind of like stay up there. And I don't know, are you referring to like space debris when you're saying that?
No, no. So the as you guys know, the Earth is centered here relative to orbits that go around the Earth where satellites operate. Um, at the altitude of the International Space Station, as an example, that's a low Earth orbit.
Mhm.
At that altitude, it's easy to get to. The launchers are going there very quickly. The launch cost economics is actually supporting that. The further out you go, so if you go, that's like 500 kilometers, you go to 1,000 kilometers, 2,000 kilometers, 5,000 kilometers. The further out you go, the longer you're going to stay up in orbit. The longer you stay up in orbit, and it's more expensive to get to, now it begins to make more sense relative to wanting to keep those platforms in those orbits. Therefore, servicing applies. The
Mhm.
best orbit, or the longest term orbit that we use all the time, is the geostationary orbit, 35,000 kilometers way out there. That's the one that most communication satellites are at, and that's the one where it makes the immediate sense to support servicing at that point. Space debris is a little bit different. Space debris could be at any orbit, sort of anywhere,
Oh,
and it is a real problem, or something to be absolutely be considered, but it's different than what I was speaking about.
thank you. So for our next question, one of your signature ideas is a satlet, which are essentially like small modular cells, each around 15 pounds, that can clump together and work as one full satellite. So it almost sounds like building a spacecraft out of like Lego bricks in orbit. So we were wondering, what is a satellite really, and why is assembling a satellite in space so much harder than it actually sounds?
Yeah, no, it's a good point. So that was the that was my investigation that I was really trying to get at when I was at DARPA. And you can think about the concept of aggregation or integration, and there's a spectrum of what the elements are that you aggregate or connect together. They go from homogeneous to heterogeneous, and what that basically means is a cell, as an example, just a propulsion cell, or is a cell a little bit of everything that goes into a satellite that you eventually connect together to make some larger satellite?
Yeah.
So the satellite idea was specifically meant to try to uncover that. Um, the I mean, the analogy that I've always used to me, the most fascinating thing is us. And if you look at us, the biological entities that are humans, um, there's basically a couple of handfuls of key cells that create muscles and nerves, transport mechanisms for blood, etc. And those key cells then make up millions that these amazing complex, objects that we sitting in front of here, right? Um, the idea was to, is there a way to change how we build satellites in orbit such that once things get up there, now you have the ability with no gravity. You don't have the launch problems of forces that are given to it, which drives most of the design of a spacecraft is just to get it up there. Once it's up there, then the question becomes, can you send other things up to add to it? Because there's really no limit to physical size or volume of things in space.
Yeah.
So that was really the idea behind it. The fascinating thing is that this notion of a satellite is really about what you consider modularity.
Hmm.
So, as an example, the laptops or the computers we're working today, you can think of them that they have modular components. You take a mouse and you plug it in, and automatically the laptop recognizes it's a mouse and then runs programs to allow you to use it. So you've just aggregated something to that laptop. That's a modular approach. So the idea was, can you apply that to space? And the fascinating thing about that is that it begins to address this notion of sustainable elements.
Yeah.
Same thing with cars. When I was younger, I had a 1967 Mustang. Loved the car, and used to always go and find new sort of components. You put a new wheel on, right? Or you can add a blower to the engine, right? The that the mechanisms to do that were the designs that enabled modularity to support that. It also meant that when something broke down, I can go replace it. That's sustainability based upon modularity, based upon the design practice or principle that you can integrate and connect things after you've actually bought it or it's been created. So I was just trying to translate that into space.
Thank you.
Uh, I wanted to discuss your work at Arkisys. I'm sorry if I'm pronouncing that wrong. But you're building something called the port. So it's kind of like a seaport in orbit where a spacecraft can dock, get refueled or repaired, drop off and pick up cargo, or even get built, like we discussed before. You said the technology to pull this off mostly exists already, and it's really an integration challenge. What would a working port in space actually change, and what's the hardest point of getting to that point, getting to that goal?
Yeah, no, it's a good question. The concept behind using the analogy of a nautical port is really this idea that you have a constant set of arrivals and departures to a location, and at that location, which on the Earth is typically located in unique harbors based upon the landmass, and then you build up this thing called a port, which allows cargo to come in, services to be executed and provided, commerce to essentially flourish. So the concept is, if we really want to get to that kind of cadence, if you will, or activities in space, then we're trying to translate that, as we call ourselves, or call the primary element that we have, the port module. And the port module, again, the precept is you can aggregate additional port modules together in orbit to create a larger sort of floating platform in space, which now means you can actually do more things, whether it's manufacturing, whether it's refueling spacecraft, whether it's repairing, having a repair station, all the things that enable sustainability and maintainability over time, now translated into space. But there's a location in space, specifically, i.e., the ports, that can support that. So that's the reasoning behind it.
Thank you.
So early in your career, a lot of your work was in propulsion, testing thrusters, and even a miniature lunar lander. That's pretty far from robotics and satellite servicing. What pulled you toward this second generation space direction, and did anything from that early propulsion work end up carrying over?
Yeah, it was interesting. I was lucky enough to have been able to go to Russia years and years ago after the they had their what they called October Revolution and was attempting to move into more democratic states, and to do testing inside laboratories where they had honestly perfected what was called then the Hall thruster. Interesting concept. The as a part of that investigation, the lab that I went into actually had created a single propulsion module that had the tanks with the xenon and the thruster itself and the electronics to run it. So it was sort of, honestly thinking back on it now that you asked the question, that was one of the first times that I've seen there's an integrated element that you can take that somebody builds and you can stick it into a spacecraft. So it's a bit of a modularity approach, if you will. Um, uh, that that the as I sort of went through different parts of the career, yeah, you mentioned the lunar lander that we did, the ACAT test, which was so much fun. Honestly, got in so much trouble, but it was great fun. Um, the idea was to take something that had been designed as a kinetic kill vehicle specifically, and that's what it was designed for, but translate it to a new domain or a new functionality or new use. And that was, can you take the advances in miniature propulsion that kill vehicles had actually pioneered, and then put that into a new, can we replace or demonstrate what that would have done had we had it when we went back to the moon. So again, the idea was, the first idea from the Russia was sort of modularity. Maybe that's where it was. The ACAT test, or the prototype lunar lander test, was how can you take something that was designed for one particular. And so I tend to think that in some way that those kinds of things were sort of setting me up for thinking about this notion of modularity and aggregation and changing functionality, etc. I just didn't know it at the time, I guess.
For our next question, back around 2000, before satellite servicing was really an industry, you helped run a startup in Germany called Vanguard Space, which is one of the very first companies trying to make a business out of repairing and refueling satellites in orbit. So that's an idea that the space world is only catching up to 25 years later. So we were wondering, what was it like chasing something that early, and what did betting on an idea ahead of its time really teach you?
Yeah, that was a yes. It was great fun while it lasted until there was no more money, and then had to get a real job. Um, it so it was interesting because we were truly pioneering that concept of the initial ideas of sustainability, and the reasoning behind it actually was driven by economics. That was the principal driver. So every spacecraft that goes up, or most spacecraft that go up, especially if they're large, they get insurance. Makes sense, right? You want to insure in case the launch vehicle blows up, in case something goes wrong, before you get the money making element, which is a satellite, into orbit. So we started with the insurance companies and said, hey, um, uh, you know, the one of the big challenges at the time was a launch vehicle would put a spacecraft into orbit, but it was the wrong orbit. And but the spacecraft is perfectly fine. It works great. It's just not in the right orbit because the launch vehicle failed to get it there. The insurance industry had a right then to pay out to the company. Well, it's a total loss, even though the spacecraft is perfectly functional, but it's not in the right orbit. So it can't make the money. It can't do what it was supposed to do. So we went to the insurance companies and said, hey, we have an option. If you allow us, put a rider on the insurance policy that says, before you write off that satellite as being complete loss, let us, a space servicing company, so you didn't hear about them, go up to it and move it to the right orbit. Simple, very straightforward, right? It's
Yeah.
almost like a tow truck service. That was the first thought for it.
Hmm.
Um, so that there was a lot of interest, and the interest was only, well, that'll save us a lot of money. So as an example, if the satellite was insured for $100 million, we would charge only $50 million. So the insurance industry would save 50, the company would actually get their money back, and so everybody would win, right?
Hmm.
The challenge was that nobody had done it. That was very, very, very early in the stages of sort of technology. So, that was a really tough sell. It was a great experience, but in the end, it was ahead of its time, as you guys said.
Thank you. Yeah, that sounds like a experience.
And to wrap up, we wanted to end with a question that's aimed towards our audience. So, if a student watching this is genuinely curious about space, robotics, or the field of aerospace, what's one concrete thing you think they could do this week to start exploring it?
Buy a Raspberry Pi, look up Arduinos. There are so many really low cost things that you could put together for $100 today, literally, to begin to explore the idea of Python programming, which again is accessible to almost everybody today, to connect to some kind of a servo that begins to demonstrate it. The interesting thing about space is if you forget the domain, which is tough and rough to get into, which you'll eventually learn, everything else can be done. And you can do everything from COTS components on the ground, things you could literally buy at Amazon, or you can go, to Best Buy and get a bunch of stuff. So that would be, honestly, that'd be my recommendation. All these things, everything that you hear about relative to, well, space, you have to study all these things, which is true if you want to understand the environment. But the fundamental precepts today are that almost everything that works on the ground, you're able to translate into space, and you could start working on it today, literally.
Thank you so much.
Thank you
Yeah,
so
yeah,
much.
yeah,
Yeah.
yeah,
Thank you.
yeah.